Of all the platonic solids, the dodecahedron has gotta be my favorite one. Of course, Nintendo R&D 3 took the cube as their inspiration for the 2001 classic, the Game Cube, but it's not to be outdone by the other consoles with their iconic shapes, like the Xbox prototype and the PlayStation. Well, I guess most of the time they aren't named after what their plastic shell looks like, but at the very least every console worth its weight in salt is distinguishable from its silhouette alone. But it's common knowledge that the best consoles aren't the ones that look the coolest or have the most compute power or even the best commercials. No, the best consoles are the ones that had fun games running on whatever hardware was available to them, no matter how limiting it might have been. While the earliest consoles were still fairly primitive computers, by the 2010s, consoles weren't running on kilobytes of RAM anymore. Their hardware was often better than a standard home computer. Maybe not if you were a tech guy, but your PS3 was by far more advanced than your aunt's Dell Inspiron. But the 2010s also saw the introduction of a new kind of machine with some good enough compute power.
The little single-board computer.
Which at the beginning was another way of saying Raspberry Pi. I remember getting into Pi Mania myself. Everyone had to get their hands on one. Dads were getting them for birthdays, kids were getting them for Christmas. My grandma even gave me one for Chinese New Year. At least she probably would have if she were Chinese. Actually, I remember buying my first Pi. I was at Micro Center in 2016. There was a whole stack of those magical Raspberry Pi 3s that I had heard everyone talking about. So bright-eyed and full of hope, I bought one, brought it home, booted it up, and then promptly went outside. The thing about Pi Mania was that I think for every 3 Pis sold, 1 got used and 2 got relegated to the drawer. This is the exact Pi that I bought at Micro Center 10 years ago. I've never used this in a project even once. So today I'm finally going to turn this thing into a proper gaming machine. And I'm not talking about the #1 suggestion in 10 Things to Do with a Raspberry Pi article, because my browser can pull up any game in seconds. I don't need a dedicated machine to do it slower. And if you think about it, the Raspberry Pi is basically already a game console. You just need to connect it to power and a display and then plug in the game card, the SD card. If you use the Pi normally, this SD card probably contains a full-fat OS. But for my purposes, it could also be a bare metal program that directly executes on the CPU. Just add some arcade buttons, speakers, and a bigger cartridge slot for good measure, and that's my platonic ideal of a game console. Also, I want it to be a dodecahedron. I printed this giant model to show myself that a uniform dodecahedron would be way too big and I would need to squish it down so it could be smaller, like a handheld, and I convinced myself of the exact opposite. I love this thing. It's honestly really comfortable to hold. I've added this black rectangle here to represent the screen, so I think if I add buttons to this panel on the left and right here, speakers down below, and the cartridge slot up on top, that would make a pretty good interface for everything. I want to go with only arcade-style buttons instead of a D-pad or a joystick, kind of like those fighting box controllers. Of course, it won't be any good as a fighting box, not least of which because it has 6 too many sides, but because I don't want to go with the professional low-latency arcade buttons, since I like the look of the concave arcade buttons much better. Also, can we just take a minute to appreciate the Chinese word for concave? In total, I want 12 of these buttons connected to the Pi, so each button will have one foot tied to one of the Pi's GPIO pins, and the other tied to a power pin, making each button a basic switch circuit. Now, in the analog world, the button won't go from straight on to straight off. It'll be pretty bouncy. From designing a keyboard from scratch, one thing I've learned is that hardware debounce is going to be a lot more effective than software debounce. That means adding a little resistor and capacitor to each button, which does stabilize things fairly well, but what I really need is a Schmitt trigger. This is a device that has an upper threshold and a lower threshold, with the signal only switching high when the signal goes above the upper threshold and only switching low when it goes below the lower threshold, giving super clean output. Component-wise, I can use a 74HC14D chip, which has a total of 6 Schmitt trigger buffers, so I only need 2 of these on the board. And I know the Pi can be powered through the 5-volt power pins, but that bypasses the fuses, and I'd rather not risk killing my Pi when it's already patiently waited 10 years for some action. Instead, I'll add a USB-C to USB-C power bridge with another switch in the center so that I can flip the console on and off. For simplicity, I'll put all the circuitry on the same PCB with JST connectors for the switches and a 40-pin header on the bottom of the board. And to get the full game console experience, I want some kind of SD card extender so I can plug in some fancy cartridges, similar to how Abe from Abe's Projects did it when he made his Ship x86 console. Wait, actually, those carts are just using SD cards too. That's perfect. Maybe I can steal that.
Hey Abe, how's it going?
Hey man, it's going good. How are you?
Good. I'm making a Raspberry Pi console. So you know your Ship x86 console you made?
Uh-huh.
Do you think I could borrow that design you had for your cartridges?
No.
Then I noticed the repo was open source, so I didn't even have to ask for permission in the first place. There are two main parts to this design: the carts themselves, which makes the 10 pins on the microSD card large enough to fit into this 40-pin connector, and then the second board which houses the connector and adapts the SD card to USB. Since the Raspberry Pi only needs the original SD card signals, I've modified the second board to connect these signals to just another JST connector, which will allow the SD card extender that I found to plug into one end here and the other into the Pi's SD card slot. All three of these pieces will be manufactured by PCBWay, who are sponsoring today's video. You all know PCBWay for their excellent PCB services. Super easy to customize the board color, or for boards like the game cart, specify the exact thickness that I need. But I also like to use their PCB assembly services to place all my incredibly tiny surface mount components for me. Of course, my JST connectors are through-hole parts for better stability, and those are no problem either. So for any PCB prototyping, part assembly, CNCing, or 3D printing that you need to do, head on over to PCBWay using the link down below to get started. And while that's off being made, I can start working on the software side of things. But first, I realized that I've never seen what happens if you power on a Raspberry Pi without an SD card in it. Nothing. That makes sense. The Raspberry Pi doesn't use UEFI firmware like your PC does. Once the board receives power, it's actually the GPU part of the SoC that wakes up first and runs the embedded bootloader program, which looks around for the SD card, finds and executes the file called bootcode.bin in the root directory, which initializes RAM, then loads fixup.dat to configure memory mapping, then runs the start.elf program, which wakes up the rest of the hardware, reads config.txt to set the specific hardware parameters, loads kernel.image into memory, and finally kicks the CPU awake to start running the OS. From a bare metal perspective, that whole startup process and associated startup files provided from BigBerry can stay the same. But instead of loading and executing the Linux kernel, I can load my own program to run instead. There's two main schools of thought when it comes to bare metal programming: those who still cling to the ways of the operating system and continue to write their code in C, or dare I say, C++, and those who embrace the CPU for what it truly is and write their code in assembly. Although ARM assembly isn't very friendly. It's nominally RISC, but anyone that has spent any time working directly with the ISA will tell you that that doesn't mean anything. I'm not talking about how ARM doesn't stand for Advanced/Acorn RISC Machine anymore. It just means ARM, by the way. I mean that there's a lot of interesting conventions in ARM assembly, like pre- and post-indexing, conditional execution, inline shifting, adding S to set flags, and sure, these features are useful, can make the assembly code take up fewer lines, and can add some efficiency to execution, but in my opinion, they ruin the spirit of RISC. Compared with the x86-64 ISA's nearly 4,000 instructions, ARM's only over 1,000 instructions seem like they really are the slimmer option here. But compared with a 6502's total of 150 opcodes, that's opcodes not mnemonics, of which there are only 56, it really seems like for ARM, RISC is more of a marketing thing nowadays. Which it is. And wouldn't you know it, ARM instructions get decoded down into micro-ops anyways, so it really isn't any simpler for the CPU to execute. So don't listen to anyone online that says RISC is the reason ARM chips are power efficient. No, ARM chips are efficient because they were designed that way so they could go into mobile devices without sucking the battery dry in 2 minutes. It has nothing to do with the ISA. Luckily though, at the end of the day, Zipf's law still applies, and most programs are made up of the load and store register instructions, move, and the basic math and binary logic instructions, with everything else making the occasional cameo whenever it's useful. The Raspberry Pi 3 uses a quad-core Broadcom BCM2837 64-bit SoC with ARM v8 Cortex-A53 cores. After the aforementioned boot process, the CPU begins execution at the designated start address, 8000. And because it's quad-core, the first thing to do in the program is to check the ID of the core and make it go to sleep if it's not core 0. Then after finishing the housekeeping chores like cleaning the BSS section, the CPU is free to do whatever. Starting out, I'm going to be following a tutorial I found from Low Levels channel on youtube.com, so I'll start by setting up the GPIO pins. In this system, the registers that control the pins are located from 3F to 000000298. This address will be different if using a Pi 4 or 5 instead. The first 3 registers use 3 bits for each of the 30 programmable pins to assign its function. Assigning 1 here will set it to output. Then there are separate registers for setting and clearing the output pins, which, if delayed a little, should flick an attached LED on and off. This code is compiled using the new compiler tools targeting ARM, with the executable program being called kernel7.image. So I'll just copy the startup files and the kernel placed onto an SD card, then plug that in, connect the specified pins to the LED circuit, and power it up. Awesome. Again, that was all from Low Level's tutorial video, and while this is bare metal control of the GPIO pins, the program is using AArch32 or 32-bit ARM instructions, but this is a 64-bit processor, so it's time to go 64-bit. The main difference between AArch32 and AArch64 is that the former has 15 general-purpose 32-bit registers, while the latter has 31 general-purpose 64-bit registers, with SP being a separate register and LR becoming X30. Though these registers can also function as 32-bit registers using W0 to W30. Why didn't they just go with R0 to R30? Well, it was specifically so that anyone who would be converting code from 32-bit to 64-bit would have a terrible time meticulously replacing R's with W's, because you just can't search and replace all for one of the most common letters in the alphabet. Otherwise, the compiling process remains the same, except now using the 64-bit compilers instead of the 32-bit versions. And I need to add one more line in config.txt, arm64bit equals 1. Lastly, be aware that the program now starts at memory address 80000 instead of 8000, so update the linker script accordingly. Can you tell it's 64-bit now? Since I already have my PCB designed, I know exactly which I/O pins my buttons are going to connect to. So this init button pins function here will set the pins to input mode, and then they should probably default to it, but just in case, this code sets them to be pulled down according to the required timing to do that. Then to read the output from these pins, I can just check the GP level register and then store those relevant values in a button status buffer for easier access later on. The Pi 3 was the last Pi to feature the standard HDMI port. None of that weak micro HDMI you'd get on the later Pi 4 and Pi 5. But I'm not going to be using this. I'm going to be using the display serial interface over here, using this screen. This is a Waveshare 4.3-inch 800 by 480 touch display that I can screw the Pi onto the back of. Then here's that SD card extender, and then the DSI cable comes right in on the top. Let me boot up with Raspbian quickly to make sure everything is working. As for using the game console with an OS installed, I do plan on having a startup script that will be running to turn the button input from the I/O pins into keyboard output. That way I can play any game I want. That does not look good at all. I'm just going to assume this is a power issue since it's the only micro USB cable I could find, and I know it's not a very good one. I think it might stabilize with better power circuitry later on, hopefully. Back to the bare metal code. In order to access the graphics stack to output to the screen, I have to say please, or rather I have to write a letter to the GPU stating the resolution and color depth of the display, and place it in the GPU's mailbox at memory address 3F00B880. Then once the GPU reads the mail, it'll write a response over the top of my mail character buffer, which will contain, among other things, the frame buffer address. With this address, the CPU can directly plot RGBA values onto the screen. Actually, this is a little ambiguous, I'm realizing. I don't want you to think that's what the default splash screen is. Hang on a second. Okay, there we go. This shows that it's mine. The big question with the dodecahedron is, how do I put the guts in here? I think the easiest way would be to split it in half down the edges, then keep most of the space on the inside hollow. But this really is ginormous. Pretty much too big for all but the biggest printers, and while I don't think anyone should make their own, I do want to leave that option on the table. So I think that separating each face of the dodecahedron into its own slice is probably the easiest way to go. Plus, there are only a few different types of faces to make. One for the screen, the left buttons, right buttons, 2 for the speakers, 1 for the cartridge slot, and then the back are all blank pentagons. But how to connect all these pieces? My first thought was dovetails, but I've been down that route before with limited success. So I think a series of pins and holes will probably hold everything together. That's feeling pretty solid. So with pins on one side and holes on the other of each pentagonal prism, I can make a ring around the bottom pentagon. Then for the top half of the dodecahedron, put pins on the top to mesh with these holes on the bottom half. I've actually printed these in resin using the Form 4. The process of SLA printing is a little different from FDM printing. For one, since it doesn't deposit material but just hardens the resin on each layer, print timing only really depends on how tall it is. So you can squeeze as much as you can onto one print bed, and it won't take any more time than just printing that tallest model. The layer thickness can also go down to 0.5 millimeters, which, as you can see from this little Entei model, shows off the amazing details you can get. Look at these clouds. If I didn't know this was 3D printed, I don't think I'd suspect it was. Formlabs did send me this printer, but no money changed hands here. I'm not a paid op. And even though the post-processing is much more work in the end, I think the quality is much closer to that of an injection molded part. So a couple of years ago, I wrote a version of Pac-Man in ARM assembly for Android. And while a phone is different than a Pi, code is code, especially assembly code, and it didn't take too much to port it over. I specifically wrote it so that it would be easy to port, because all I have to do is run the initialization function, then run the logic function every tick, passing in the joystick input, and then I can output the game's graphics buffer it generates onto the Pi's screen. On the back end, Pac-Man is running more or less like it would on an old arcade, with sprite tiles being moved around the background. Though the ghosts don't follow their standard AI, but they do have random movement thanks to the SoC's hardware random number generator, which uses the entropy of thermal noise to generate randomness. After some initialization to kickstart it running, random words are able to be read from the address 3F104008. Joystick input for the game is also tied to 4 of the arcade buttons, with another button tied to rerunning the initialization function when pressed, which will reset the game. This should be it, so we'll see how it works when everything arrives. It must be Boxing Day because everything I need is in my box right here. I got my buttons, wires, speakers, and of course the PCB straight from PCBWay, the game carts, the SD card adapter, and the Pi hat. Although I asked them to leave the 40-pin connector unsoldered because that's my dessert. For sure it looks worse than if I left it to the professionals, but I don't know, it could be the lead fumes or something else, but I just feel very satisfied doing this. This looks brilliant. Let me put in this program, and let's hope there's no smoke here. Alright, here we go. Now this isn't Pac-Man, it's a little program I whipped up to test whether all my buttons are functioning correctly. And it looks like everything's working. That's amazing, that's everything I could have hoped for. I love it when it comes together like this. Now this is what everything has been building up to. Some bare metal Pac-Man action. Alright, that's awesome. Buttons are working, timing is going alright, no OS in sight. And this button here should be reset. Ooh, I don't think that'll ever get old. Now, how about a regular OS and using the arcade buttons for input? Well, I don't think this is going to work out. I guess it just needs too much power or something? I don't know. All my bare metal programming was just fine, though I'm only using one core for that. But I am hitting it pretty hard though, so I really don't know what's going on here. and RetroPie is working just fine. Actually, surprisingly well for how bad Raspberry Pi OS was doing, especially because RetroPie is literally just Raspbian with emulators installed. Now, I did write my own script to take the button input and have keyboard output, but RetroPie also has some built-in tools to use the GPIO pins for controllers, so that wasn't actually necessary. Regardless, I'll post that script and the rest of my bare metal assembly on GitHub for you to check out. Now, bare metal is by far much faster to load and execute, obviously, but for playing retro games, this is not a bad machine at all. Plus, there isn't anything stopping me from having an Ubuntu cart or having another cart that has a script so that when it boots up an OS, it starts running a certain game, whether that be a Pokemon hack or a colorized Game Boy game or the best racing sim of all time. And that's really the magic of these single board computers. You plug in a new OS and it's like an entirely new machine. Don't forget to subscribe for more consoles made out of platonic solids. And if you missed it, my last Patreon and YouTube members exclusive video that I made was about that time that McDonald's made their very own clone NES and how I was the first person to ever dump that custom game that came with it.
Abe, check it out. Here's that console I made.
Oh, wow.
Yeah, it's got the arcade buttons on the side here and the cartridge slot on top.
Oh, awesome. Wait, cartridges. Are those my cartridges?
They're inspired.